Hi, this is Hunter's Reassessment for Work and Potential Energy. This go around, we're going to do the pinball machine example from class. I know you never gave a solution to it, so I'm going to go ahead and give it a shot. We're going to start out by, on the left hand side, we're going to use our formulas that we can use in work energy problems. We've got K equals 1/2 mv squared. For kinetic, we've got U elastic is equal to 1/2 kx squared, where k is the spring constant, and U gravity is equal to mgy or mgh. Now, in any one of these problems, the first thing we're going to go ahead and do is we're going to define our system. And in this pinball machine, we're going to define the system as the spring plus the ball plus the earth. Now, on the right hand side over here, what I have is I have the radius of the ball, the mass of the ball, the distance x, which if you look at U elastic, x is the distance a spring will compress. We have the angle in theta is 15 degrees. We have the main distance of the table is 1.6 meters. The distance of the ball is the radius times 2, so that's 4 centimeters, which converts to 0.04 meters. And we have the total of the two for the length is 1.64 meters. That's the distance of the ball plus the distance of the table. And what we're going to be looking to find is when we compress the spring, when we pull the spring back and compress it and then we release it, we need the ball to travel 1.6 meters up the table in order to get past its distance so you can play the pinball game. But we also have to add in the width of the ball, or the diameter of the ball, which is 4 centimeters. So if you look right here on this part of it, if you look right here is the ball, and it starts at the line and it goes from here to here. That would be 1.6. So the ball has to pass completely past that 1.6 on the backside. That's why we need to add that point, that 4 centimeters. Okay, so what I'm going to do now is I'm going to go ahead and I'm going to set up my equation, find out what I can use and what I can't use, what I need and what I don't. So I set it up, K initial plus potential, which is U, elastic plus potential gravity, U gravity initial, is equal to K final plus U elastic final plus U gravitational final. Now over here to the right, I've went ahead and etched these out. The initial velocity, which K is equal to mass times velocity squared, 1/2 mass velocity squared right there. So we got that, and at the very beginning when you pull the ball back, it doesn't have any velocity. It's sitting still, so therefore it's equal to 0. Then we've got U elastic is equal to 1/2 kx squared, where k is the spring constant and x is the distance of the spring compression. Now, U gravity initial, we're going to set that to 0 because it's at the bottom of the table. It's at the bottom. Right now, as our reference point goes, there's no potential. We've got velocity final, or k final, is going to be 0 because in this situation it's going to go to 0 at the end of its trip up. We're going to have potential elastic is going to be equal to 0 because at that point the spring's been released and all the potential energy is gone, and U potential gravity is going to be final, is going to be mgh. So we go ahead and start doing, I guess, what we would call the physics on this problem. And we set it up right here. And then we say, well, all we have left is potential elastic, and potential gravity. So then we substitute into it. Then we solve for K, because that's what we're looking for, is the spring constant. And then we go ahead and plug in our numbers. Now, and then we're going to get our answer. Then it was meters squared per meter squared right here. And since we're looking for a spring constant, which is newtons per meter, we're going to go ahead and cancel one of these meters out on top and bottom. That gives us kilograms per meter per second squared. That's a newton per meter. So we got 282 newton meters. Now the solution you gave on the Moodle is 28.2 newton meters. I went through this over and over. I can't find where I may have a discrepancy in my measurements conversion. So I think the actual number is more correctly 282 newton meters. But if that's not correct, let me know, and I'd be happy to listen to why it's not correct. Thank you.